Hello and welcome to AIAIART Lesson 9 on Evolutionary Algorithms and Compositional Pattern-Producing Neural Networks. So today is going to be different for a couple of reasons. One, we're going to be departing briefly from the overall type of algorithms that we've looked at throughout the course. Everything up until this point has been based around this idea of optimization via some form of gradient descent. So we're going to be taking a break from that and looking at some different types of algorithms. But then we'll come back, we'll examine a couple of sort of tangential topics and then wrap up not just the lesson for today, but the whole of this course. So I think this is going to be the last lesson, at least for now. So I'm excited about covering the content, but also a little sad that it's all ending. But without further ado, let's look at today and then specifically, why is this interesting and why have I chosen to include this at the end of this course, even though it's a bit of a deviation from our previous path. So one way you can think about learning methods in general is that what we're trying to do is find a good or an optimal point in parameter space, right? It's ultimately kind of a search problem. And so when you're framing it like that, you say that, okay, well, some operations, they don't have nice gradients, and so we can't just smoothly move throughout the loss landscape, if you will. So there's certain types of functions that don't differentiate nicely, and so these gradient-based methods have issues with those. Sometimes you don't even want like a fixed number of parameters. So our parameter space, we might not want the restriction that we get when we're trying to set it up in a more traditional, deep learning-based style. And then also there's philosophical ideas about, maybe the kinds of solutions we can get to via gradient descent are just only a small subset of the total possible solutions, or even the possible good solutions. So those methods might be holding us back from some breakthrough. And then some other reasons, nature doesn't do stochastic gradient descent, right? We have examples all around us of creatures or organisms that look fairly well optimized, but it's through a different process. And change is fun. We might be getting a little bit bored with the same old optimization loop. And most importantly, I think evolutionary computation just sounds really cool. So with those kind of hand-wavy justifications for why we should look at that in hand, let's dive into the topic. And if you're running along with me, save a copy of the notebook in your Google Drive, connect up, and we can start running through and you can follow along. Nothing in this notebook needs even a GPU, and it should all run fairly quickly. So don't worry about resources there. Okay, so like I said, in nature we see some amazing examples of organisms that seem really well optimized. And so when we talk about evolutionary algorithms, these are in many cases just directly inspired by the natural processes that we see in action, right? These mechanisms by which we get complexity through this sort of repeated series of steps that is survival of the fittest, natural selection, however you'd like to call it. And so when we talk about genetic algorithms, what we're trying to do is we're trying to mimic that process. And for that to happen, we need a few things in place. So first, we need some sort of measure, right? Some sort of fitness function that's saying if we're trying to reach some goal, and you don't always want to optimize towards some objective, but generally you've got an idea, we'd like to do this task or this thing with this precision. So we need some objective function, we call it, that's going to give us a measure of fitness. And then we need a population of individuals, which is going to be defined by, you can call it a genome or their DNA, their parameters, that give these sort of individuals or these genomes some properties, and we have a way of evaluating those against our fitness function. And so if we want to mimic nature, we're going to say we'll start with a population, right? And often in the simulations, we start with just a completely randomized population. And then we're going to select the ones that are fitter, but with some randomness. And then we're going to kind of mutate or change those. And in nature, you have, random mutations to the genes from cosmic rays or whatever, but you also have this idea of recombination via sexual selection. So a lot of genetic algorithms try to incorporate both of those. And we're going to repeat this again and again and again. And so while we do this, there's a number of things to consider. What kind of population do we start with, right? Is it completely random, or do we sort of restrict it to some sort of more likely locations? How do we measure fitness? How do we tweak the genomes generation to generation, right? What do our mutations look like? Is it flipping a single bit in some sort of binary representation of the genome? Is it adding a node in a graph, how do we make these changes? How random will we be in our selection criteria? Are there additional things we would want to encourage, like maybe species diversity or simplicity of the network? And then when do we stop? Do we just go for as many iterations as we can? Do we have some sort of desired fitness that we define as our stopping point? Or do we do just a set number of iterations? So all of those are things you can explore. I mentioned in the live stream, this is kind of a classic rabbit hole, right? Because even just given this hand-wavy introduction, you can start to think of ways you might try this on your own. And I highly recommend that as a learning experiment. But for today, we're not going to do anything like that from scratch. We're instead just going to lean on this existing implementation called Python Neat, right? Based on an incredible paper that I highly recommend reading from a man called Kenneth Stanley, I believe. And we'll take a look at that paper once we start digging into how this works. But I think maybe let's quickly start running the demo, and then we can talk about what's going on underneath. So the task we're going to try and solve here is a simple demo. This is taken straight from the Python Neat documentation. We would like to create an exclusive OR gate, right? So if both inputs are 0 or both inputs are 1, we would like our outputs to be 0. But if only one of the inputs is a 1, either or, we would like the output to be a 1. So in this case, we're specifying, well, this is our desired inputs and outputs. So our fitness function, right, that we're going to define here is going to say how closely do the outputs of the network match our desired outputs given the particular inputs, right? So it's just a very simple, in this case, it's the squared difference, right? You might recognize, oh, like a mean squared error. And the only thing that might catch you out is that in gradient-based optimization, we often talk about minimizing a loss, whereas in evolutionary algorithms, we usually talk about maximizing a fitness or maximizing some objective function. So the signs on your loss/objective might change, but the general idea is the same. We have some metric. We'd like to get it as good as possible, which in this case means high. So 4 minus whatever our squared error is means that the higher it is, the lower the error. And then we're going to define what's going on in a configuration file, which we'll look at. We'll set up some recording, and then we'll plot the outputs. So this shouldn't take too long to run. And while it does, there we go, finished already. We've reached our maximum fitness or our desired fitness in a relatively small number of iterations. So what's going on here? What is NEAT, right? This neuroevolution of algorithmic topologies, I think it stands for. What's happening? How are we defining this behavior? And how is it learning or evolving? And so we can, first of all, we can look at the output, right? And it's this network, which it turns out in the NEAT sort of framing is defined as a kind of set of nodes, right? Each of which has an activation function, a means of aggregating the inputs to this node, an extra bias and response variable, and then it produces some output. And so we're always going to have two inputs because that's what we specify for this task, right? Nodes -2 and -1. And then we specify some number of connections. And these connections have a weight associated with them, and they can also be enabled or disabled by random mutations, right? So you could go and take a piece of paper and you could say, you know, this input here goes to node 154, right, which is this node specified here. It also goes into node 229. Node 154 feeds into the output, so does node 786. You know, so you could kind of draw out this network diagram. And if you go and check out the original paper, which was linked earlier in the notebook, you can see the background of this, right? We have each network that we're trying to evolve is specified by some genome, right? And this is going to contain exactly that information that we saw printed out. What are the nodes and what are the connections? And when we're mutating these genomes, we're able to do a number of different types of mutation. We can add nodes, we can add connections, we can change the types of activations, we can change the weights, we can change the response variables, and so on. Enable and disable various things. And so those are the kinds of mutations that are happening. As to how that behavior itself is specified in a particular run, well, that comes back to the configuration file shown here. So I link the documentation for Python Neat about these configuration files, but you can see there's a few things that we specify. We'd like to try and, you know, pick the max fitness. When our maximum fitness gets above this threshold, that's when we'll stop. How many genomes are there in our population? What's the default activation? We can specify different options. How often does it mutate? what are the different aggregation options, how often do those mutate, how do we initialize things, how often do we add or remove connections, and so on. So you can really kind of go highly in depth, tweaking all of those parameters and getting different behaviors. But yeah, it's quite fun to see. This is the outputs from a previous run. So this was a run that took a lot more generations. And so you can see it kind of starts out with this kind of random mapping. This is a grid from 0 to 1. If you check out the code, we're just going from 0 to 1 in 32 steps for visualization. And so what we'd expect is that we'd like a high output for 0, 0 and no, is that right? For 0, 0 and 1, 1. But we'd like I'm going blank because I'm recording. Yeah, for 0, 0 and 1, 1, we'd like low outputs, and for 0, 1 and 1, 0, we'd like high outputs. So we kind of like, ideally, this diagonal to be high. And so it starts out completely wrong. The error is very high, right? The fitness is low. And then over time, it gets slightly better and slightly better. And it morphs into this new network, right, defined by these nodes and connections, which can now give us the desired behavior, right? Low outputs in the cases where it should be low, high outputs in the cases where it should be high. And so if you run this, you can replace these numbers and investigate any of the save files that you're particularly interested in, right? So you could say, you know, show me I'll just very quickly try it with this new run and see what that looks like. But then once you're done, oh, that's bad. I did mess up the notebook a little bit during the live stream last night. So apologies if there's any issues there. I will try and clean it up after this recording as well. Okay, so I've now deleted the save files, but you can see here, starts out pretty random, and over time we get a situation where it's high in both of the areas it should be, low in both of the others. And you can see it's now learned a very different function to the previous example. And so this is one of the things with these evolutionary algorithms, because there's so much randomness, you're not guaranteed to get the same solution each time. And that can be quite interesting. So what can we evolve beyond this kind of toy demo example, right? And the answer is pretty much anything, but there are some practical limitations in terms of how large of a network you might want to be dealing with when you've only got limited computation. So we're going to take a look now at one class of algorithms, again, sprung up from the same guy, Kenneth Stanley, and many others working on the project. And it's nice because this tied in some questions we'd had as to topics that people would like covered in the course, as well as feeding in, you know, I mean, Sebastian Risi is a researcher who does mostly self-organizing systems, and so these have also come up in the domain of, you know, cellular automata and things, which we talked about last week. And it ties together some sort of modern fancy network architectures. So it's kind of nice because this all kind of brings these different topics together into the same domain in a way. So these pretty pictures were produced by a particular style of algorithm, right? So the type of network is called a Compositional Pattern-Producing Network. Highly recommend checking out the paper that was linked there as the one that sort of introduced it. But then also look at the kind of background on the PickBreeder project, which is where these actual images are from. Sadly, the original website's down at the moment, but you can check out a sort of re-implementation of it here. And so this is a network that takes in an X and a Y coordinate and it outputs a color, right? And so just like these sort of simpler networks that we looked at with the NEAT and so on. Sorry, I've lost my paper here. Yeah, so it will look similar to this. We've got, again, the same library being used. We're adding nodes. Each node has a different activation function. But in the case of these ones, we have a whole library of different activation functions kind of tuned to produce these sort of visually interesting images. And the neat thing is with PickBreeder, they used human beings as kind of the fitness function, right? You can select which members of the population you'd like to mutate and evolve. And each time you get now, you know, new variations on those, you can pick the ones that you like. And the original PickBreeder project was collaborative. And so I might evolve to some point and I say, oh, I quite like this. I give it a name, people could rate it. But then someone else could come and start from that genome and continue evolving from there. And so you could get these sort of really interesting collaborative sort of many generations of evolution happening on the internet together as a community. So over time, people were able to evolve these different sort of creatures. Where's some examples here in the paper? Here we go. So these are the ones pictured in the tweet. People collaborate to end up with some pretty fun and interesting patterns. And each of these is still a fairly simple network at the heart, and quite fun to go and explore the genomes and see the network diagrams. But anyway, so we're going to try and create some like this. So the configuration file is going to look slightly different. We're going to specify different maximum fitness, and I'll explain how we measure. I'm using a slightly larger population. And now we're using a number of different activation functions as our available ones, with some probability of replacing that activation function each time. You can add additional aggregation options as well. And in fact, I think here's a list of some of the activation functions available. So if we write this configuration file, we can start playing around. Now there's an extra bit of code here. One of the issues with these networks, so like I said, a CPNN is going to be evaluated for every XY coordinate. So if you want to produce a 32 by 32 pixel image, you'll evaluate it once for every coordinate in a 0 to 1 grid with 32 coordinates in each row. And if you're doing that for larger images in sort of native Python, it can get quite slow. And so PyTorch Neat is a project. I forked it from an additional repo, but the original didn't have very many activation functions implemented. So we're just going to steal some code, modify it. And all this is doing is it's turning those networks into kind of PyTorch modules, if you will, which we can then run many inputs through simultaneously, take advantage of the speed up that comes from all of the parallelism and linear algebra magic that PyTorch gives. So it's not strictly essential, it's just a speed up, which means we can do more generations, larger populations, and so on. But besides that, this is going to look fairly similar. We're going to eventually do our run based on our configuration file. But as our objective, I thought as a sort of minimal demo, we can just keep making some random, so this is creating a new population from that configuration. And every time I run this, we see some random outputs. And when I find one I like, the kind of task, the simplified demo task that I've made up is to say, can I now re-evolve something that looks like this, right? Starting from a fresh population. And so to do that, we're just going to say, well, this is going to be my target image, right? And I'm now going to take the mean squared error between whatever my actual image looks like and this target image. And that's going to be my fitness, right? I'm going to do 1 minus that to be my fitness. So closer to 1 means lower error. And then we're going to try and evolve towards, minimizing this difference or maximizing this fitness, if you will. We'd like to try and re-evolve a pattern that looks like this. And so this is pretty much the same code as before, creating a population, keeping track of things, saving every 5 generations, and then let's run it for at least 50 generations. And then once we do, this is from the previous run, so I'll rerun this here. Once we do, we should see it starting from something that's fairly bad, and over time getting better and better and better. And what's interesting is, at least from the times I've run this demo before, if you print out the genome of the sort of winning genome from this run and compare it to the one that you're trying to match, it's quite often it's not the same network, right? It's got a slightly different architecture, but you can see it starts out not too bad, but definitely not the same as our target. And yet over time, it gets better and better and better at sort of at least attempting to reproduce the target image. So you can see it's not an exact match, but it's pretty close. And so that's a sort of fun, contrived demo. Again, showing a slightly more complicated task. We're trying to arrive at an image. But in this case, we know that it's one that's at least in theory possible because the image itself was generated by another of these same networks. So I hope that's useful. Now you can try, I've left as an exercise here, can you add a more complicated loss function, right? Maybe you'd like to match an actual real-life image with one of these CPNNs, or maybe you'd like to evolve towards a sort of text description using clip. That can be really fun. I've tried it myself. I struggled to get anything super coherent, and that's probably due to just not really knowing or not really having time to explore the whole space of parameters, what size population, how many nodes should we start with, etc. But you can see this was the prompt ripples, candle flame, green and blue square. And so, it is able to slowly get more like a text prompt. But if you do manage to create something more complex, like if you can get a face or a dolphin, then I'd love to hear about it. So please do reach out. If you're interested in examples of evolutionary algorithms, do check out the EvoJax project, is where there's probably a lot of work happening at the moment. So they include their implementation of something called ESClip, which you can also see this paper, Modern Evolutionary Strategies for Creativity. And they show a case of something that would be quite hard to do differentiably, right? Stacking triangles. You can think of maybe some hacks with differentiable drawing to try and do that, but it's something that's very well suited to an evolutionary approach. And if you check out the EvoJax project, I think they've just yesterday released a new paper. So I don't even know if it'll pitch up on the GitHub here, but they also have some other examples: evolving motion, solving tasks, multi-agent simulations, little game playing robots, and so on. So it is an active area of research. There are non-trivial examples of evolutionary algorithms being used today. In fact, I think there's been some really great work looking at supply chain logistics and things like that, and solving them with this modern neuroevolution in an accelerated way. So it is an active research and it's quite fun, but our little demos here maybe haven't shown it in the best light. Nonetheless, that's the end of our little recce into evolutionary algorithms. But now I'd like to take specifically some of the ideas of these compositional pattern-producing networks, right? These networks that can take in basically just a coordinate and output an image. Why are they interesting, and can we bring these back and marry them with our, more traditional deep learning ideas of gradient descent and so on? So it turns out we can. And why would we want to? Well, there's a couple of advantages of them. Number one is we kind of here, if you think of these networks, right, this is a simple network with some number of nodes or some sort of, it's a mathematical function in a sense that takes in X and Y and spits out red, green, and blue. And nowhere in here is there any reference to resolution, right? So we're not dealing with an image that has 32 pixels by 32 pixels. We're just dealing with a sort of infinite resolution mathematical function. And we can pass in higher and higher, sort of closer together, X and Y points. We'll still be able to evaluate this function at each point. So it gives us kind of a nice resolution-independent representation of an image. And so that's a task that's been approached in the deep learning world as well, right? People have asked the question in various ways: how do we find a sort of implicit representation of a signal like an image or a sound, where we just parameterize that signal as a function of spatial coordinates or time, and try and replicate that with a set of learned weights. So you can do this with a simple linear, multi-layer perceptual network that gives you a number of parameters to optimize. But it turns out that these aren't great at capturing the kind of high frequency detail we see in natural signals. And so Siren, right, which is this paper here and then improved on in a second follow-up work, these Siren networks say, well, what if we use a periodic activation function, right? We use something like a sinusoid of different frequencies with learnable parameters. Maybe that'll help us capture both the low frequency structure and the high frequency detail that we need to truly represent these kind of natural signals. So let's dig into an example of playing around with Siren, and then we can kind of see how it works just by exploring the code and the different components. So the implementation we're using here comes from a developer called Lucid Rains, right? I think Philip Wang. Incredible, prolific developer. If you see a new paper out, it takes like 24 hours for him to have a new repository up with at least sort of the rough workings of the code. And then very quickly after that, him and then many other members of the community come together to kind of reproduce these research findings. So huge props to Lucid Rains for doing this and many other really cool PyTorch implementations of papers and techniques that we see in research. Okay, so with this library, we're then going to quickly build or look at a Siren network, but we're going to first look at the individual components. So at the base, we have an activation function, which is just a wrapper around torch.sign, right? We have some frequency, and then when we pass in some numbers, in this case 2 random numbers, we'll get a sine of those numbers multiplied by some frequency plus some phase offset optionally. And so you can see 2 inputs, 2 outputs. This is just an activation function. If we gave it 5 inputs, we get 5 outputs. And so then this is the activation function used of now our siren layer, which is, you can think of as kind of like a linear layer, except that the activation function is going to be a sinusoid. And so now when we pass in some number of inputs, we can specify how many are we going to get some number of outputs. Right? And this layer in particular is going to have some number of parameters associated with it. And so if we want to see that, maybe let's just see the shape of the parameters. And let's have a look to see, so this has some number of parameters, right? There's 3 inputs, 256 outputs. So we have a 3 by 256 matrix plus 256 bias values or phase offsets. I'm not sure how to interpret them in this particular case. But the point is, this is a layer with learnable parameters. And so we can produce an output via a network made up of many of these layers. And then we can update these parameters using our good old friend gradient descent. So the next level up from one of these layers is a Siren network. We specify 2 inputs for X and Y, how many neurons we'll have in our hidden layers, how many layers we're going to have, and how many outputs. In this case, we're doing red, green, and blue outputs. Plus sort of frequency, initial frequency to set, and you can play around with that for different types of signal. And then we can see this in action. So now when you pass in, X and Y pair, we're going to get red, green, and blue out, right? And I should mention something I didn't emphasize very well in the live stream. These Siren networks are used more generically, right? It's not just images that they can represent. You can imagine parameterizing a sound as a function that has one input, right, time, and a single output or 2 outputs if it's stereo sound. You could represent a video as X, Y, and T as your input parameters. You could represent a 3D scene where you have maybe like a density field or a sign distance function. So your input would now be X, Y, and Z. Maybe your output is some sort of measure to the nearest surface or a color. So they're much more sort of general purpose than I made out in the live lesson. Okay, so let's try and fit an image to this one, because that's the framing we're using. And we can take a look at the image here, and I'm also turning it into a tensor, just to be in the format that the Siren wrapper expects. And so quite appropriately, I thought it's a picture of a siren, although if you Google for pictures of sirens, you'll have to search a little bit to find one of these and not the other kind, but I leave that as an exercise for the reader. Okay, and then our optimization loop is going to be very simple, because LucidRains also has this kind of wrapper object that lets us pass in a target image, and it's going to handle, producing an image from the Siren network, comparing it to that target image, and it's just going to feed us back our loss, and then we can use this to update our parameters, right, the net's parameters. So I'll quickly run this. Let me actually change this back to a smaller number of a smaller hidden dimension, because we are running on CPU, and I don't want this to take forever to run. And then as that fits, you could also try tweaking using fewer parameters, or exploring larger and smaller networks. But the idea is that after some number of iterations, we've converged on a representation where, by passing in the X and Y coordinates of every pixel in this image, we are going to get out something that resembles the desired target image, right? In this case, you can see it's not an ideal representation, but the neat thing is, this is incorrect, this is from a later demo. The neat thing is that this representation, we can kind of decide how compressed it's going to be, right? So you can see here, if this image is 256 by 256 pixels, that's several 100,000 parameters. If you imagine it being represented, one value for each red, green, and blue channel at each pixel, whereas our network here only has 17,000 parameters, right? And you could maybe play with settings for omega 0 and number of hidden layers and so on, see if you could get an even sharper, sort of more high fidelity representation. But the nice thing is our network here is kind of scale independent, right? So we can put a new wrapper at a different image size. We can view that straight away, and it's not going to be, the signal is going to be the same, the number of parameters is going to be the same, and we have complete control over that, right? So in this little demo here, if we set the number of hidden dimensions to only 16 and only use 3 layers, we get a very bad representation, right? It's not ideal at all, but it's only 643 parameters. And so what this Siren representation has given us is complete control over how complex of a representation we'd like. And then it also has all of these additional benefits, right? Infinite resolution, it's scale independent. And also because this is continuous, it's meaningful to talk about, the gradient of the color with respect to position, right? Because it's all just a mathematical function. It's not binned into pixel values or anything like that. And so it behaves really nicely when you're trying to now talk about, differentiating some parameter across the image. Cool, so I hope that's interesting. If you'd like to play around with, or what can we do with this kind of implementation, I should probably run these two. You can see, or you can try yourself using clip again, or some other method to try and steer this towards something more abstract than just a single image. I also did share this link here to a separate notebook where you can do, a clip description or a text description. Using clip, we're going to compare the image generated with the Siren network versus our sort of text description, and over time you're going to be able to generate these fairly pretty images. It's quite fun to watch it go. So here's a couple of my first sort of rough tests. And I should mention that the parameters, the size of the network, all of that is completely thumb-sucked at the moment. So you should definitely experiment with changing all of these parameters and seeing how good you can get. I have a feeling that this might be quite a fun technique. It definitely lends itself to, especially these kind of like underwater scenes are perfect because it's got this kind of shimmery caustic look because of the nature of how the image is being made as this kind of stacked series of sinusoids. So I think it's pretty cool. In terms of like artistic applications, you can see because these Siren networks, we run them once for every pixel. That's a style that lends itself very well to something like a compute shader. So in this case here, I used a clip prompt of fiery glowing dragon scales. And instead of just 2 inputs, X and Y, I trained it with some sort of additional latent inputs. And it has to try and look like the prompt across all of those inputs. And so you kind of get this dynamic warping, moving effect, pretty cool. In a similar vein, but more complicated, this is by an artist called Mario Klingelman. Pretty incredible demo. And so this is all a Siren network, right? It's just a series of sinusoids evaluated for each XY position, plus some additional extra controls. And this is all running in real time in the browser. And you can see here, these are the parameters of our Siren network, right? It's all just sines of different inputs. And so it's quite a lot of parameters, but it's definitely something manageable for a modern day. I mean, this is my integrated graphics on my old CPU, on my old laptop. So very, very fun field. Blackell-Mori is one of the people who kind of pioneered these sirens in shaders. So go check out her YouTube channel there. And then finally, I just think like these kind of weird, warpy, glittery effects from these are quite compelling. So I did even try training a Siren network as a generative network to try and, generate not just one image, but multiple. Never quite got it working perfectly, but, the results are at least different, right? You can see this is something that isn't just your standard VQGAN plus clip. So that's quite fun. All right, I'm aware that even this video is going on in time. The live lesson at this point was like more than an hour in. But I just wanted to touch finally on this one additional topic which ties really well in with the rest of the stuff that we've covered today in this lesson. But we're not going to have time to actually dive into our own implementation. There's various reasons why I didn't want to do that. Partly this is just a very active field, right? There's new research coming out all the time because it's such a hot topic. And also the implementations tend to be, either very involved to code or very slow. But let's just cover the idea. So these things called NeRFs, you've probably seen them in the news, where you've seen these really cool kind of 3D flybys or visualizations. And so what is it? Well, remember we said in this section, we're representing an image as a function that takes in an XY coordinate and spits out a color. And so the question that NeRFs tries to answer is, how do we represent a 3D scene in this implicit way, right? How can we learn some function that kind of parameterizes this 3D scene? And so the idea here, and this diagram, which is taken from a blog post linked just below, This kind of encapsulates the answer, which is to say, well, what if we have the same idea, right? A network, like Siren or like a normal MLP or some other architecture, and it's going to take as inputs a spatial location, X, Y, and Z, and a viewing direction. And it's going to output something called the radiance field. It's going to output a color, but also a density, right? So this is kind of like, okay, we have this volume, right? X, Y, and Z. Maybe you can imagine like a cube of space. And for every point, for every direction, it's gonna give us a color and a density. And we can use this to now render views of this volume from different angles, right? Because if you want to see it looking from one side, we can then trace rays into this volume. And at multiple points along that ray, we know our view direction, we know our coordinate, we can get back a color and a density. And if the density is very low, we're not going to see much of that color. But if we hit a high density patch, that's going to then be mostly what we see. And so this is a really nice framing of the task. And what it means if we, in terms of training data, like how do we train one of these networks? Well, we often have, we can take photographs from multiple angles, right? And so for each of these photographs, we know the viewing angle and so on. And so if we now like projecting these back, or we're rendering our volume from those viewpoints, which are like our ground truths, we can then update the parameters of this network so that the rendered view kind of matches those input images. So we're trying to learn this representation. It's done, originally with quite a lot of different views, right? Like quite a large amount of training data, lots of work done on how can we use very few images to generate a whole radiance field, lots of work on how we do this very computationally efficiently, lots of work on how do we do this for, larger scenes and so on. But the core idea is to say some network, right? Some black box network, and you see standard MLPs used, you see, much fancier kind of weird architectures, some with, frequency domain components, sort of like Siren, others with, all sorts of extra tricks. But the idea is that we'd like to say, given an arbitrary location and a view direction, give me a color and a density. So that's the core idea behind NeRF. If you'd like to learn more, 2 Minute Papers has a few different videos on these, very, very nice, kind of very visual and interesting summaries of the ideas. This blog post I found a good comprehensive introduction. Here is a good implementation if you're interested in reading code that does something very similar to the original NeRF paper. Another good implementation if you're someone who's a fan of JAX, and this is where I stole the diagram above. And then more recently, like if you check out some of the work that NVIDIA has been doing on their so-called neural graphics primitives and their instant NeRFs, you can see some of like the current or close to current state of the art. If you check out the series of tweets from Scott, you'll see again a bunch of linked papers on trying to solve these additional problems, right? The original NeRF was really good for small bounded scenes, right? But people have been asking, well, how do we represent large areas? What if we have, multiple adjacent blocks, each represented by their own learned radiance field? What if we have, scenes with lots of backgrounds, 360 views? We have this MIP NeRF paper that's able to give us, these really lovely representations. And I think they use a separate network for the background and the foreground and for depth. Block NeRF, sticking many, many blocks together. So there's lots and lots of active research in this field. You're welcome to, go check out some of those, but hopefully you can still use our kind of intuition of, okay, this is still a CPNN in a way, right? This is still something that takes in a location, some parameterization of space and optionally view direction, and it gives me out a color. And there's modifications that let you also, parameterize the light direction and all these other things. Very, very nice, neat, useful class of algorithms. Okay, so I think that's about all I wanted to cover there. So all that's left is to say, I think this is the end of at least part 2 of AIAIART, but it's definitely not the end of this channel or this Discord. So if you have ideas of what you'd like to see next, please do come along. There's active discussion in the Discord of if you're working on your own projects or you've got particular research questions. I'd love to discuss those. But if you've got ideas of like, oh, I'd love to see a video exploring the ethics of AIAIART and what that looks like, or particular topics that weren't covered in the course so far, then I'm definitely open to covering those. And then on the Data Science Castnet channel, I'll still be putting out videos and projects. They just probably won't be sort of designed to fall within the larger structure of the course, right? So I'll have a bit more freedom, I think, to, dive into JAX more deeply or other libraries that aren't kind of in line with the PyTorch and AIART focus of the course. But yeah, it's open and evolving. So I look forward to seeing you in the future, both here on YouTube and in the Discord. But for now, thank you so much for coming along on this journey. I hope you've learned a fair bit. And yeah, we'll see you in the future.